the topics on layer 2. So particularly we are looking at framing and error detection, encoding. Okay, that's not part of the today's discussion. Before we go into the details of the link layer issues, so let's quickly recall the network link. So when we say network link, the link or the communication medium which is used to connect two systems. When we say systems, it could be the routers, switches, or hosts. That means our computers, our phone, or let's say servers, etc. Different physical media are used to propagate signals. So when we say bits are sent, actually the signals are sent, and there are different types of cables or medium we use, both wired as well as wireless. And duplex links are used in switched networks. Meaning is that in a switched network, let's say when A and B are connected, we use the symbol like this without any arrow. So this is a duplex link or full duplex link. When we say full duplex, that A can communicate to B, at the same time B can communicate to A at the same time. But usually how it is implemented is, it's implemented as two different fibers. So if you consider the switched networks, present day switched networks, okay, say for example wide area network or backbone or anything, the fibers which are connecting two switches or routers, so they are used for data communication in both directions. Okay. We use two fibers, one from A to B, the other one from B to A. This together we call it as a duplex link. Okay. But in other local area environment, we might use off duplex, okay, particularly in Ethernet, etc. Twisted, okay, these are some of the examples. Twisted pair copper wire. So this is something similar to the telephone cable. Okay. We are not going into the characteristics, very specifics of physical characteristics and other things, but as a network engineer, you should be knowing that there exist different types of cables which are used in networks. Okay. So we have Cat5 cables and all. Sometimes you might have seen. On the other side, the cables which are rolling on the big wheel kind of things, Cat5, okay, kind of cables. Coaxial cable can also be used. So good example is the TV cables, so which is basically a coaxial cable, but they are all based on the copper. There's copper wires, and we also use fibers for communication, particularly for long distance as well as high speed, high data rate communications in GBPS, etc. We use wireless link as well to communicate between two nodes. The examples are terrestrial radio channels, maybe on the earth, wireless LAN, then cellular network. Okay, so these are all examples of wireless communication. And similarly, we can also communicate through satellites, okay, between countries, or as a backup if something fails on earth, we can use satellite as well for communication. And this table shows features of some of the important cables and fibers. Okay. Again, as I said, as a network engineer, okay, so you should be familiar with these kind of features. So when we say cables or links, okay, the two questions arise. What is the data rate, or what is the capacity it can provide? Okay, and how long the communication can take place without requiring any amplifiers or anything. Okay. Because for short distance communication, we can use some type of cables. For long distance communication, we may need other types of cables. You don't need to memorize these numbers, okay, but you need to be aware that different cables differ in their capacity or bandwidth and distance. For example, if you consider Cat5 or category 5 twisted pair copper wire, similar to the telephone cables or LAN cables, okay, they can be used to provide capacity of, let's say, 100 Mbps, can support up to a distance of 100 meters. So if you want to connect two switches up to 100 meters, you can go for Cat5 cables. Okay. Then we have two kinds of coaxial cables, thin coaxial cables and thick coaxial cables. Thin coaxial cables and thick both can be used to support 100 Mbps, okay, data communication, but they differ in the distance supported. For thin coaxial cables, of course, they differ in their other physical characteristics. We are not going into the details. Thin coaxial cable can be used to connect systems within 200 meters. This can support up to 500 meters. And if you look at the fibers, there are two types of fibers in use, multi-mode fibers and single mode fibers. Multi-mode fibers, okay, they are usually used for a short distance communication. Okay. They support up to, let's say, 100 Mbps. So maybe within a lab or office we can use it, but within a small campus also we can use it. It can support data communication up to 2 kilometers. So within the whole building or a small company to connect multiple switches in different floors, we can use multi-mode fibers. But multi-mode fibers are cheaper compared to single mode fibers. Single mode fibers, but they can support higher bandwidth, 10 Gbps, 40 Gbps, etc. And they can also support communication up to 40 kilometers. That means usually on the wide area network or metropolitan area network, the link length would be definitely more than 40 kilometers. So for every 40 kilometers, we may need what is called optical regenerators or amplifiers. Okay, so up to 40 kilometers, we don't need any amplifier or regenerator. That's what it says. Now we can also look at the link from another perspective. Okay, how the links can be leased out from the service providers. Okay, so if you take any network infrastructure in any country, usually already the network is in place, or the fibers are laid out under the ground. Okay, maybe different countries could be connected by fibers under the sea also, right? But within the country, that usually government or maybe government controlled or owned body, okay, would be responsible for the networks and other things. Is that okay? But those networks or channels or bandwidth would be leased out to the service providers by the government. Say for example, maybe in Singapore IMDA, okay, may consider leasing out, okay, the wireless channels and other things, okay, to different service providers. So service providers make use of these links and networks, but from the service providers, others, they can lease out to others as well. Okay. Anyway, let's not go into such details, but we have seen this type of links in the first lecture, last mile links. Last mile links means or first mile links, which are the links used to connect to the users. That's the first link or last link. Okay, a good example is the broadband network which we have at home, right? Fiber broadband network, Wi-Fi. Okay, so this kind of networks, they are called last mile networks, which I mean the service providers usually provide a link to connect to our home. Okay, so we can get internet service through this link. It could be ADSL or cable modem based or the fiber broadband, so which we discussed at length as part of lecture notes 1, so I will not be repeating that. Okay, this is one type of links which we can subscribe. Okay, which we don't call it as lease out here, but which we can subscribe to the service provider. So for every month we pay $40, around $40, $60, depending on how much bandwidth you are using, 500 Mbps or 1 Gbps, 2 Gbps, etc. Right? On the other hand, there exist other type of links in practice which we call them as leased links. So these leased links, they are used to connect normally an arbitrary pair of nodes. That means you take, for example, the ADSL or fiber broadband. Usually our home, we connect it to the service provider network, right? We have fiber broadband, we connect to the service provider network. We don't have a link to connect, let's say, our home to your friend's home, and we cannot directly have a link connecting our home and friend home or parent's home, right? We should connect to the service provider. But if you look at the companies or organizations, they might have multiple branches, so they may want to have a link leased, okay, from the network provider, okay, to connect any pair of switches. Okay, so in that case, they need to lease out link from the service provider. Usually, organizations they do. Okay. So what type of links they lease out? In practice, nowadays there are two types of links which can be leased out: DS links and OC links. DS stands for Digital Signal Hierarchy. It all started from the old telephone network. So if you look at the telephone network, for one voice communication, if you want to communicate to the other party through the telephone network, not through the broadband or internet, okay, we need 64 kbps. That comes from the sampling theorem and our voice signal bandwidth, etc. So I'm not going into that mathematical details. But if you look at the telephone network, okay, there are many 64 kbps links, okay, from individual home. Okay, so 1000 homes are there. We cannot connect, okay, we cannot have a cable, telephone cable connecting all 1000 pairs, all 1000 homes. Instead, what we do is we have a multiplexer. So this is DS0, this is, so a number of DS0 signals can be multiplexed into DS1. How many are multiplexed? Let's not go into the details, okay? So that means DS0 signal means the cable from your home, 64 kbps. Okay. So at some point, okay, they are all multiplexed, from multiple homes are multiplexed into DS1. Similarly, a number of DS1 will be multiplexed into DS2, DS3 and all. Commercially, DS2 is not in use. I am also not sure why DS2 is not there, but DS3 link is available, okay, then DS4. Okay. Accordingly, we have the links which we call them as T1 link, T3 link, etc. And in Europe and Asia, we have E1 link, E3 link. North America, we call them as T1 link, T3 link. Okay. You need to know that there exist, okay, some links which can be leased out, which come with some data rates or bandwidth. Okay, you don't need to memorize the table again. In the test or exam, any numbers are required, I will provide the numbers for these tables. So DS1 bandwidth, that means if you lease out a T1 link, the bandwidth is 1.544 Mbps. Okay, so you can imagine how many telephone connections can be multiplexed onto that. Okay. For data connections also, 1.544 looks small, but maybe if you look at the history, when it evolved several years ago, okay, so that was seen as reasonably good bandwidth. Okay, then comes T3 link, which comes 44.736. Again, don't worry about these magic numbers. We don't have time to discuss how we get all these numbers. Okay. So we have T4 link as well, but anyway, I'm not listing all those things. Later evolved what is called the OC links, which is based on SONET, okay, synchronous optical network. Equivalently, we have STH, synchronous digital hierarchy. Synchronous digital hierarchy, STH and SONET are similar networks, similar standards. SONET is used in North America, STH is used in Europe and Asia. Okay. But concept-wise, there are many close similarities. So whatever we discuss about the SONET, okay, we are not going into much details, but at a high level, these discussions are relevant for STH as well. Okay. It uses TDM, time division multiplexing, fixed TDM, and here the transmission is in the optical form when it's transmitted, when it's propagating through the optical fiber. But when you prepare the frame and other things at the end node, it is in electrical form. So the frames are in electrical form, the packets are frames. Then when it is transmitted, it is in the optical form. We give two different names, okay, maybe in the context of SONET. When it is in the electrical domain, electrical signal forms, high volt, high 1, 0, etc. We call it as STS signal, synchronous transport signal. When it is in the optical form, we call it as OC, optical carrier. Okay. So we have different levels of multiplexing, time division multiplexing, OC1, OC3, OC12, etc. Okay. So that means we can have a multiplexer which can multiplex, let's say, 3 OC1 signals into one OC3 signal or one OC3 link. Okay. So these are the bandwidth associated with every link. OC1 51.84, OC3 155.52. Again, you need to memorize it. There is no OC2, there is no OC4, 5, 6 and all. Then we jump to OC12, 622. Then very recently, commercially, we have about 40 Gbps link, which we call it as OC768. And interestingly, if you multiply this by 3, when you multiply OC1 by 3, exactly you get this. 3 into 4, 12. So if you multiply this, you get this. Similarly, if you multiply this by 12, if you multiply OC1 rate by 12, you get OC12 rate. Similarly, if you multiply OC1 rate by 768, you will get this. Or you take OC3, you multiply this by 4, you will get this. So this is possible because of the TDM and the clocks are synchronized, etc. Other features are there, but that doesn't happen for T1 link or T3 link. But for this, if you know the rate for OC1, that is 51.84 Mbps, how we get this 51.84, this magic number, slightly later we will see. Okay. So these kind of links, they provide dedicated bandwidth. The bandwidth is dedicated, not like our home. Our home, okay, though we say it's 1 Gbps, okay, we have 1 Gbps link, and if you look at carefully, they say up to 1 Gbps, right? It's up to 1 Gbps, not 1 Gbps, okay? And they may say under these ideal conditions, this, you get 1 Gbps. It may not happen, okay, because at some point, okay, there could be shared also. It depends on the peak demand, and there are other factors which affect this. But this type of leased links, when you connect, let's say that we have offices for an organization, you want to lease out to connect these two offices with, let's say, OC, OC 192 link, then 10 Gbps is guaranteed for that link. Okay, let's move on to the next topic. We are going to look at the relationship between bandwidth and channel capacity. So if you can recall from the first lecture, so I've been using these terminologies, okay, bandwidth of a link, capacity of the link, data rate of the link, right? Link capacity, link bandwidth, link data rate, bit rate. So there are many terminologies. So, and also I've been insisting that or emphasizing that in network context, we use these terms many times interchangeably. When you say link bandwidth 100 Mbps, actually I refer to link data rate, okay, because bandwidth is measured in hertz, the capacity as well as the data rate, it should be, the unit is bits per second, okay, because these two are related. When you say you are transmitting bits, okay, the propagating as a signal, okay, signal bandwidth is required, right? So what is the relationship between the capacity? Capacity is the maximum data rate. Let's say you are given a link, okay, it doesn't mean that you can transmit at any rate, 10 Mbps, 10 Gbps, 100 Gbps, may not be possible. For a given link or given communication channel with certain bandwidth, you can go the data rate up to certain limit. The maximum data rate is the capacity. The relationship between capacity and the bandwidth, okay, is defined by this theorem. We are not going into how we derive this, but this is the result. C capacity equal to B multiplied by log to the base 2 1 plus signal to noise ratio. Signal to noise ratio is that, okay, you transmit a signal, it propagates through the link. When it is received, okay, noise gets added through the communication. You don't get the pure signal at the other side, okay. So the ratio between the signal strength and the noise strength or power, okay, between signal and noise power, that is called signal to noise ratio, S over N, okay. If S over N, basically S over N defines the quality of the channel or quality of the link, okay. We expect S over N be very high. That means signal quality, signal power should be high compared to noise. correct? And it depends on the medium, distance. So there are several factors which affects the signal to noise ratio. Okay? And this is the relationship. We consider a simple example, dial-up modem. Of course, this is an outdated modem. I think I briefly mentioned to you. So when we started using internet from home and all, we used to have dial-up modem. Okay, that is our PC at home that comes with the telephone socket, like the telephone socket on the wall, right? Okay. So if you want to connect to the internet, then you should remove the telephone cable from your receiver, and then you connect it to the computer. Okay. Now computer for the network, it doesn't know. Okay, it's connected to the receiver or to the computer. Okay. So there's a modem inside. So whatever data you type, okay, to send it to the internet or this, so that will be modulated or converted to mimic a voice signal kind of things. So when it goes out, this is something like a voice signal. Okay. So at the other side, when we say modulator modem, it's a modulator as well as demodulator, right? Similarly, when you send data, receive data, the voice signal kind of signal will be received, then that has to be converted into the bits. Okay? And it's very slow in kbps. I think that's what I was mentioning. We used to get few kbps, not mbps, kbps. Many times 1 kbps or even less than that as well. So we can use it for some simple email, text or browsing. And also you need to pay the telephone service provider, Singtel, okay, based on the usage. Because Singtel doesn't know whether you are using it for your computer or for the telephone. Okay, as if you are talking over the phone for 1 hour, you have to pay. Okay. Anyway, that's a history, but this example still it's relevant. Okay, this example we can use it for communication through optical or communication through coaxial cable, through the cable medium or anything. So if you look at the voice signal, when we speak, okay, so it has many frequency components. We generate signals. Okay, so that is usually in the range 300 hertz to 3300 hertz. Okay, whether male voice or female voice. Okay, generally this is the range. Okay, so if you have a filter, okay, you can limit to, let's say, 3300 or 3000 or 4000 maybe in the worst case. Okay, so you can use band limited signal at this end. Then you can use A to D converter and other things to sample it to send the bits. Okay, that's a different story. But what is important here is that, as a simplistic example, we assume bandwidth is about 3000 hertz. The width of the frequency band is 3000 hertz. Now we are going to calculate the channel capacity. So maximum at what rate we can transmit data through this. Okay. Assume that this is a practical one. The signal to noise ratio is 30 dB for the voice link. Okay. So we use dB notation. dB notation, I think you must be familiar. dB is x plus 10 log base 10 x, some signal to noise ratio. So that means 30 dB is equal to 10 log. So it is 30 dB, but it's not the actual number. The unit is converted into dB, decibel. Okay. So 10 log S over n base 10. So 10, this cancel 3. So S over n is equal to 10 cube approximately. Not approximately, right? Exactly. Okay. This is 1000. So S over n is 1000. 30 dB means signal to noise ratio is 1000. You can imagine signal strength is 1000 times noise strength, something like that. Okay. So now use this form here. B is the bandwidth, 3000 hertz. Log 2, 1 plus S over n. S over n is 1000. So 1 plus S over n is 1001. Okay, but it is base 2. 1001 is approximately equal to 2 raised to the power 10, correct? Approximately, because 2 raised to the power 10 is 1024. just we are making an approximate calculation for a quick calculation. So if it is 2 raised to the power 10, this because it's base 2, so log 2 raised to the power 10 is 10, 10 into 3000 is 30K. So dial-up modem capacity is 30K. So actually the commercial one was slightly more, okay, it's around 56, I think it's 56K. Yeah. But this formula is relevant for other type of communication through coaxial cable or fiber or anything. Next, yes. Oh, this is the frequency range. When we speak, okay, the significant frequency components are 300 hertz to 3300 hertz. So when you plot it, the frequency spectrum, we consider the width. This one, this. Yeah, so you can assume that bandwidth is 3000 hertz. But in practice, we generally allow up to 4000. See, this actually can, I mean, I don't know whether if you have studied communications, basic communications, you might be knowing. So there are many frequencies components. Other frequency components may not be significant when we speak, when we generate the signal. Okay? But for telephone, actually, we band limit to actually 4000 actually. We use 4000 hertz to be safe side, to accommodate more. Instead of 3000, you can use 4000, should be okay. But not more than 4000. I don't think the voice signal bandwidth would be more than 4000. So in the test or exam, okay, any channel or link is given, okay. So some quantities will be given. We have signal quality, signal over noise, we have capacity in bits per second, we have bandwidth in hertz. If two quantities are given, you should be able to calculate the third quantity, right? It's not difficult to calculate. Is that fine? And note that maybe only in this context we talk about bandwidth as well as channel capacity in the right sense, with the right meaning. Okay? That's why I mentioned in the lecture notes that depending on the context, you try to find out. If you say something hertz, then it refers to true bandwidth. Let's say the bandwidth is 8 megahertz. Let's say I'm using TV channel bandwidth. Okay, for example, you take cable modem. Cable modem, we have been using it until recently from the Starhub, right? So when we use cable modem to get internet access, we use channel frequency. Let's say we use 8 megahertz channel bandwidth for communication. That 8 megahertz is the bandwidth, right? Then depending on the signal quality and other things or link quality, you can calculate what's the maximum rate which we can get. So that has a limit, right? So if you look at cable modem, we used to go about 25 Mbps or 50 Mbps. Sorry. Yeah, maybe 100, right? Not like 500 or 1 Gbps and all. The next topic is encoding. So we are not discussing this topic here in this course, because there are many topics which I added later, like VLAN, wireless LAN and other things. Unfortunately, I have to omit this topic, but I can briefly mention what it is, just to know what is encoding. When we say encoding is the mapping of bits to signals. How bits are mapped to a signal. In other words, how 0 is transmitted, how bit 1 is transmitted. So when we say the adapter transmits bits 0 and 1, okay, how it is transmitted? The simplest case is 0 means low signal, okay, 1 means high signal. That's the simplest way, right? See, for example, when you transmit 0, 0, 1, 0, 0, so you can transmit low, low, high, 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 something like this. Okay? So the mapping of bit to signal is called encoding. But this type of simple communication, okay, this is called non-return to zero. Okay, I'm not going into the details. So it's not good for network communication. Could be used maybe within a computer or disk or something, right? But it's not preferred. Why it's not preferred? One good reason is that, let's say we want to send a long sequence of ones. We want to send 10,000 ones. Let's say our packet, we are transmitting all ones. When you transmit all ones, you will be transmitting high signal all the time, high, okay? So when it is propagating through the other one, when the other network adapter receives that, the receiver may get confused where the bit begins, because there is no transition. All are flat, high signal continuously is received. High signal is continuously received. So the receiver may find it difficult to identify, okay, this is the beginning of bit 1, this is the beginning of bit 2, bit 3. So it may miss out some bits. It may miss out some bits, or it may accumulate more bits. You might have sent 10,000 bits, it might think 10,001 bits are received. Why? Because there is no transition. If you make sure that you always change here and there, then it will know that, okay, at this point at least there is a change. It will know that there's a new bit is here, right? And there's a change here. At least there should be some change. If there's no change, it all goes like flat 0 or flat 1, there's other problem, okay? Also, the network adapter, okay, they try to find the average value of the signals received. Based on the average value, they will decide. Okay, whether the received bit is 1 or 0. Because when you say high signal, when you send high signal, the signal may be attenuated, okay? You may not receive the full signal there. Then there will be a confusion whether it is 0 or 1. Correct? Let's say high signal means 1 volt, just an example, okay? But when you receive, maybe you might have received 800 millivolts or 700 millivolts. So if 700 millivolts is received, whether it is low or high may get confused. So that is based on some threshold. That threshold is dynamically calculated based on the long-term average. So if you keep on sending all many ones or many zeros, there will be a confusion. So based on this, there are many encoding techniques like NRZI, Manchester encoding, 4B, 5B. There are many other techniques as well. They are used. I skip this, but if you are interested to know more, you can go through the notes, right? Okay. So when I skip this, that means they are not examined. But only the Manchester encoding, this we will discuss in the context of Ethernet, which uses this encoding a bit, just to know what it is, okay, how 1 is sent, how 0 is sent. Okay, let's move on to the next topic. This is a link level function, framing. So first you may imagine why we need such functions. Okay, just imagine the case. There's a sender node A which has a network adapter inside who is responsible to transmit the bits. So the bits are transmitted here. The adapter on other side is receiving the bits. So the receiving adapter receives sequence of bits. Let's say 1001010011 11001. Okay, so it keeps on receiving some bits. But now, as far as the sender is concerned, this is transmitting multiple packets. Am I correct? At layer 2, we call this packet as frame. Let's say frame 0, frame 1, frame 2, frame 3. Because the sender forms small packets, we call them as frame at layer 2. That means at layer 2, when you add, let's say, Ethernet header or anything, that packet we call it as frame. That's what we discussed in lecture notes 2, right? But when the adapter receives the bits, how does the receiving adapter know that starting from this bit to this bit, let's say this is frame 0, this to this is frame 1, how does it know? Because it's receiving all ones and zeros, right? So the receiver should know the boundary to recognize that these bits form one frame. These bits collectively form frame number 1. This is frame number 2, right? So we want to draw the boundary. Okay, that is framing. Framing means draw the boundary, okay, to close the border, right? So, so this question will be answered by framing. How do we recognize that this particular group of bits form a frame? In other words, we want to recognize a frame. We want to recognize the beginning and the end of the frame. How it can be done? What are the different approaches used in networks? Okay, how they compare with each other. So we are going to look at 3 popular approaches, and we also can look into why it is good. Okay, what are the limitations? Okay, it's easy to understand. Once you know why, what it is, how it works, then you can also understand the pros and cons. Okay. First, we start with sentinel-based approach. It's a very straightforward approach, interesting approach as well. Sentinel means you have the sentry or the guard, okay, or the flag. So we have a flag in the beginning of the frame, and we have another flag to mark the end of the frame. When you say flag, okay, this is for conceptually we understand. So flag means there's a special bit pattern which is sent by the adapter in the beginning of the frame. Let's say the sending adapter wants to send a frame. First, it sends a special bit pattern which will mark, okay, this is the beginning of the frame. The special bit pattern is used normally is 0 followed by 6 ones followed by 0. This is the flag, and this is used in HTLC, high level data link control protocol. Of course, we are not going into the protocol, but you should know that this approach is used in PPP, point to point protocol and all. So maybe I can give an analogy. Let's say you consider a language, C language or many languages, okay. How do you represent a string? How do you represent a string? When you write a program, okay, so let's say you want to print a string, okay, you usually use double quote, right? How are you, hello or something, right? So this is a flag, beginning flag, end flag. Why? Because we are telling the compiler of the language, let's say C compiler, okay, that, okay, this is the beginning of a string and this is the end of the string. So all the characters in between the double quote marks will form one string. That's what we are instructing it, correct? That is what is done here. Beginning sequence, end sequence. And we have the header, we have the body, the actual data payload, and we have CRC cyclic redundancy check, which we discuss later. Okay, some extra bits are added to help the receiver to detect if there are any errors or not. Then another flag is sent. Is that okay? And this is used in HTLC and PPP protocol. HTLC is a popular and widely used ISO OSI standard data link protocol. Of course, there are many variants of HTLC used in practice, like LLC, ATM, and all. Yeah. But now, what's the issue here? The issue is this. You take again the same analogy, string, to represent a string. Suppose you want to include the double quote itself inside the body of the string as one of the characters of the string. How do you do it? So if you write a string something like this, the compiler will get confused. Okay, compiler will think that this is the end of the string, correct? Then it gets one double quote, then it say there is a syntax error. There's a syntax error, missing double quote mark or something, correct? Because it doesn't have a matching one, right? So how do you include this inside a string as a valid character, not as the end of the string? How do you do that? Is my question clear? I think many languages they use the double quote mark, right? So how do you include double quote mark as a valid character, not as a end of string? Yes? Use backslash. Slash or backslash, is it? Okay. Am I correct? So this we call it as escape character. We call it as escape character, right? Then the next question is, how do you include this slash as a valid character inside? you have to use this 2 times, right? Correct? So we want to use some extra character. It's a character stuffing. We are adding some extra character to help the compiler. Okay, we are telling compiler, don't get confused. This is not the end of the string. Okay, this is the character inside the body of the string. End of the string will come later. Okay, so there are 2 approaches in HDLC. We use bit stuffing. Why we use bit stuffing? Because the special bit pattern 0 followed by 6 ones and 0 may appear inside the payload, right? We cannot tell the user that you cannot send any data where this pattern appears 0 1 1 1 0, right? So this is 0 6 ones 0, this is 0. So what happens if the body or header that has 0? So can we tell the user not to send this type of bits inside this? We cannot, right? So if this appears inside something like the double quote here, we want to avoid it. The adapter will avoid it. So what is done is it uses what is called bit stuffing. Very simple method, bit stuffing. So what it does is the sending adapter inserts 0 after 5 consecutive ones. Whenever 5 ones are transmitted, because sender is transmitting the bits, right? 0 1 1 0 0, right? If it transmits 5 ones continuously, okay, regardless of the next bit, it inserts an extra bit, that is a 0. That means it makes sure that 6 ones will not be sent continuously, except in the beginning, at the end. Is that okay? So what the receiver will do is, beginning sequence, yes, 6 ones it will receive, end it will receive. In between, whenever the receiver receives 5 consecutive ones, whenever the receiving adapter receives 5 consecutive ones, it knows that the next bit 0 is the stuffed bit, the dummy bit. So that dummy 0 will be dropped. It will be ignored by the receiver. Is that okay? So it solves the problem, but it ends up with other issues. See, for example, let's say we are sending 1000 ones. There are 1000 continuously 1 1 1 1000 ones appear inside the body. How many zeros will be inserted by the sender? Sender will insert a 0 for every 5 consecutive ones, right? So if the sender has to transmit 1000 ones, consecutive ones, how many extra zeros it will need to transmit? How many extra bits? 1000 divided by 5 equal to 200, right? So instead of transmitting 1000 bits, the sender will be transmitting 1200 bits. So that means that 200 extra bits is an overhead. It's a waste of bandwidth. It's a waste of bandwidth, right? So can we avoid it? Then we need to go for another method if you want to avoid it, right? Okay. Now we are still here, Sentinel based method, and another important protocol which uses this type of framing is PPP, which stands for point to point protocol. That's also a widely used protocol. So it was used in dial-up modem to connect our PC to the service provider, and this also used in ADSL, SONET, etc. This also can be used, right? So it's a popular protocol. Okay. So here also initially we send 0 followed by 600 is the beginning flag, end flag is the same, but this protocol is a byte oriented protocol. Byte oriented protocol means it will send in terms of bytes, integer number of bytes. So you cannot add a bit. When you add a bit, it's not a byte, right? So it will carry bits, multiples of 8 bytes in terms of bytes. So if at all you want to add, you need to add an extra byte, right? So from that perspective, we can use hex notation, because 0 followed by 6 ones 0 is 0 1 1 1 7 1 1 0 is E, 7E. So let's use the hex notation, 7E. So whenever we want to transmit data, first you will transmit 7E, end you will transmit 7E. Okay? If you want to send 7E in between, you need to use a stuffed one, extra byte, something like in a C, we use slash or backslash double quote, right? So what is done is, whenever we want to send 7E, according to the standard, we will send 7D5E. Why 7D5E? There are many combinations you can use, but this is the standard followed. Okay. Now the problem is 7D is the escape character. If you want to send 7D, instead of 7D, the sending adapter will send 7D5D. So when the receiver receives the escape character 7D, it will look into the next character. If the next character is 5D, then these two will be replaced by 7D. When it receives 7D followed by 5E, the receiver will replace these two by 7E. If it receives 7E, it understands that this is the beginning or end of the frame. Now look at this example. Let's say this is the original data which we want to send, 578A, 7E. So these are all bytes. Okay, I put it in hex notation. Okay. So what is the actual data sent by the sending adapter is this. First, it will send the flag 7E. This is 7E. Okay. Then first byte 57 is sent, 8A is sent, 7E. 7E should not be sent as it is. Otherwise, the receiver will get confused, right? That's the end of the frame. So instead of 7E, you can see 7D5E is sent. Next 0F, 7D, you can see instead of 7D, 5D is sent. Is that fine? Then 17 is sent. This 7E, we don't change it because this is the flag. This is the flag. Any doubt? So what the receiver will do, when it receives 7E, it understands this is the beginning of the frame. When it receives 7D, it looks into the next character 7D, 5E, that will be replaced by 7E. That's what the receiver will do. Similarly, when the receiver receives 7D followed by 5D, that will be replaced by 7D. Okay? Again, there are different ways, okay, like C language, why I should use the slash, why not use some other character, $? We can use $, no problem, right? Okay, but this is the standard followed in this network. The second approach is counter-based approach. So here we want to avoid, or we want to overcome the limitation of the bit stuffing or byte stuffing. We don't want to insert an extra bit or byte, right? That's unnecessary because the size of the frame becomes longer and longer, right? We don't have any control. So what it does is, it uses a field in the header which is called count, which tells the number of bytes carried in the body. How many bytes are carried in the frame? If 500 bytes are carried in the frame, we will tell the length or the size 500 here. Okay. So this is used in Ethernet as well as some old protocol DDCMP, but you need to know that at least currently Ethernet uses similar approach. Okay. So forget about this, how many bits are used here. So you can see that initially some bits, some sync bytes are sent by the adapter. The sync bytes, they mark the beginning of the frame, something like that. The sync bytes, usually they are 10, 10, 10, 10, 10 kind of thing. Whenever an adapter wants to send something, first it sends a sync byte, 10, 10, 10. This will help the receiving adapter to synchronize its clock, because even though this adapter, they run the clock at the same speed, there may be a small drift between these two clock, right? They may not be synchronized, exactly synchronized. Okay. So when, let's say you send a bit in the beginning of, let us say, the leading edge at the sender, the receiver may try to mark receive the bit may be coinciding with the leading edge, but that leading edge and this leading edge may not be synchronized, right? Is that okay? So, to help synchronize the clock, adjust the drift, the known pattern is usually sent, which is usually up, down, 1 0 1 0. So, that will help a party to sync. So, let us not worry about this. Then, okay, according to this, this is the DDCMP frame format. 8 bits are used to represent the type of class. Maybe you can just imagine it's a high priority or low priority kind of class. So, let us not worry about this. What is important here is that there is a field count which represents the number of bytes carried in the body. Okay. Now, this followed by header, body and CRC. As I said, CRC is additional bits used to help the receiver to detect whether there is any error or not. Right. So, there are 16 bits CRC bits. Now, the problem is this, okay, it overcomes the other one, because whether you send all ones, anything, does not matter. We do not add any extra bits or bytes. That means the special pattern, well, sync pattern or whatever, they can appear inside the body, it does not matter, because we tell how many bytes are carried here, count. Then what is the issue here? There is some issue. What happens if the count value is corrupted? Count value is corrupted. Let us say we are sending frames. Let us say this is frame 1, this is frame 2. Let us say the count value is 500, okay, 500, but when it is received it becomes 4090. Let us say during the propagation the count value has changed, some bits are corrupted. So, the receiver will think that there are only 490 bytes in the frame, there are only 490 bytes. So, what it will think is, okay, it will accumulate 490 bytes. So, it may think this is the end of the frame. Actually, end of the frame is here, right. So, then the next few bytes here, this may wrongly think that this is CRC, but actually CRC is here. So, the CRC test will fail. So, that means the receiver will know that something is wrong in the current frame. So, it will ignore the frame. Then it looks for the new sync patterns, it looks for the next frame. So, this frame is a bad frame, that is dropped, nothing wrong, that is fine. Okay. But now imagine this situation. Let us say there are two frames which are sent back to back, F1 and F2. Let us say 500 is the actual count, the number of bytes carried. If this 500 has changed to, let us say, 510 bytes. Earlier 500 was decreased to 490, but now during propagation some bit value has changed, some 0 has become 1, okay, and the value has increased to 510. Sender says 500, but when the receiver receives, it finds that the count shows 510. So, what the receiver will do? The receiver will receive 500 more bytes to mark the frame. So, when it receives 500 more bytes, that is actually it has received few bytes from the next frame also. It jumped into the next frame, but it does not know that it has received, okay, few bytes from the frame. It still thinks until this is a part of the current frame. Then the next 2 bytes, this will be considered as CRC, 16 bits means 2 bytes. So, when it does CRT test, okay, will say, okay, something wrong, there is an error, right. So, it understands at this point that there is an error, but it has already received few bytes in the next frame also. It does not know that it has received few bytes. So, what it will do? It will stop. It cannot stop receiving, but what it will do is it will receive the bytes, but it will ignore the bytes it will ignore the bytes until a new frame with a new sync patterns arrive. Okay. So, as a result, this adapter has dropped 2 frames, frame 1 and frame 2. In fact, it does not even know that it has received 2 frames, right. F1 was a bad frame, but F2 was a good frame, but still a good frame was also dropped, because it does not know that it has already part of the second frame. Why? Because the count value has increased. Is that fine? The third one is, clock based approach. Yes. You may ignore if the count value has increased a lot. After 510, okay, what the receiver will do, think is it is here, because the size tells about the size of the body. Okay, right. So, after 510, the next 16 bits or next 2 bytes will be considered as CRC. But yeah, okay, that's a good question. If the sync pattern appears somewhere here, that's what you are trying to say, right? So, then it will think that's the beginning of the next frame. Again, that it will end up with another problem. Another problem is another frame also will be dropped. Okay. So, when the frames are dropped, if maybe later we will see, okay, maybe in next lecture, at link level, if you do retransmission, that's fine. Okay, at link level itself, the sender will send it. If it doesn't retransmit, anyway at the higher level TCP is there. At TCP, when the end host, not the link, end of the link, the end of the entire path, the final host, this packet or frame will be missing there. Okay, so that will take care of retransmitting, but that retransmission will take from the beginning again. Is that okay? So, the application will not lose it, but unnecessarily we are losing some good frames, okay, in the middle because of the change in the count value. Okay. So, the third approach is a clock based approach that is used in SONET or STH. See, it's a very interesting one. Okay. It has a fixed time. So, what it says is all the bits and bytes, okay, which are received within 125 microsecond is considered as one frame. It's a time based or clock based. All the bits which are received within 125 microseconds will be treated as a one frame. Why? What is this magic number 125 microsecond? So, that has come from again telephone network, 8,000 samples per second. Okay, translates to okay. Let's not worry about this number. Why we use it uses 125 microsecond. That's what I guess. Okay, otherwise it can use 100 microsecond, but it's not using that. It uses 125 microsecond. So, whatever bits or the group of bits received within 125 microsecond will be considered as one frame. Now, we know that the frame time, when we say bits are received at a rate or bits are transmitted, both depend on the data rate, right, or bandwidth. We know that frame time equal to frame size divided by bandwidth. That is, the duration of the frame depends on the size of the frame and bandwidth. Correct? So, the size depends on time and bandwidth. That is, size equal to time multiplied by bandwidth. The time is fixed, 125 microsecond. But if you transmit or receive from a higher bandwidth link within the same 125 microsecond, you will be receiving more bits, right? So the size is proportional to the bandwidth. So that's very interesting point here. Okay, let's see the key concept which is used here. In SONET or STH, okay, as I said before, STS, synchronous transport signal. So that frame, the name is given in the electrical domain. In the optical domain, we call it as OC signal, optical carrier. So both are same. Okay, let's not worry about it. So let's consider the basic frame format in SONET. It uses 810 bytes. It uses 810 bytes, and usually we 810 bytes, we represent this as a two-dimensional array. Note that this is only a representation. When it is transmitted, it is transmitting bit by bit, right? So, but for pictorial, for easy understanding, we put like this. There are 9 rows and 90 columns. So total 800 bytes. The basic frame, STS1 frame, has 810 bytes, and the first 3 columns we call this as overhead. Overhead is header. Okay, in SONET terminology we call it as overhead, some extra information. Note that this basic SONET frame can carry multiple small frames or packets. This could be voice packets, or this could be ATM connections, ATM cells, etc. I am not going into that, what is inside here, because SONET was initially was used to carry the voice packets, the telephone signals, packets, voice packets. Okay. Then later, okay, you want to carry the data packets and other things. But the basic frame is this, and 2 bytes will mark as a special pattern like sync pattern. Okay. So the any adapter will look for these 2 bytes for every 125 microseconds. Within that 125 microseconds, the 2 bytes will appear. Okay. So what is the bandwidth? We know time equal to size divided by bandwidth. So bandwidth is equal to size divided by time. That is equal to 810 bytes. In terms of bits, 810 multiplied by 8. The time is 125 microsecond. If you do this calculation, you will get the magic number 51.84 Mbps. So we have seen earlier, right, this number. So OC1 link rate is 51.84 Mbps. Link in network terminology we call it as line also. Line means link. Okay, don't think it's a typo error. Line means link. Okay. Is that okay? Now, it uses TDM or time division multiplexing. So let's say you consider OC3 multiplexer. So OC3 means it takes 3 OC1 signal and it will multiplex into a high rate OC3 signal. Okay. So just imagine 810 bytes are received for every 125 microsecond from this OC1 input, and another 810 bytes are received from this input. 810 bytes are received from this input within 125 microsecond. That is one frame. Okay. So that means 3 times 810, 2430 bytes are received in 125 microseconds. And the output rate should be able, we should use the output rate such that you should be able to send out or transmit these 2430 bytes in 125 microseconds, right? So 2430 bytes in 125 microseconds. that will be the data rate or bandwidth of the output link. Okay. So, the output data rate will be 155.52, that will be exactly 3 times 51.84, that will be 155.52. So, that means if you take OC3 frames, the time is 125 microsecond because bandwidth is higher, but in terms of size, number of bytes, it is 3 times, it is a bigger frame, but in terms of the time, all are 125 microsecond. Is that clear? Similarly, if you take, as I said before, if you multiplex 12 OC1, the output will be OC12 frame. In terms of time, it is 125 microsecond because the bandwidth or data rate is 12 times. Okay, the time remains the same, but the number of bytes will become 12 times bigger. So, we call this as clock based framing. Similarly, if you multiply this by 48, that is, we can multiplex 48 OC1 to form 1 OC48, or you can multiplex 4 OC12 to form OC48, or this is 16 OC3 can become OC48. So, accordingly, if you multiply these, you will get these numbers. Okay. So, recent standards are OC768, OC1920. Any doubt so far? So, let us move on to the next topic. There is a last part, very interesting topic, how we are going to detect the error. Error detection is the functionality carried out at link level. That means for every link, okay, whenever an adapter sends some data, the receiving adapter receives so A and B, A is the sender, let us say B is the receiver. When the receiver B receives a frame, it should be able to detect whether there is any error or not. It is carried out at link level. Of course, it is also carried out layer 3 at IP router. Okay. That is a checksum which you will be studying later. Similarly, similar checksum based method is used in TCP also. So, error checking is done at multiple levels. Okay. But the strongest error detection is done at the link level. That is the strongest error detection. Strongest means, okay, it's very powerful technique. It should be able to detect most of the errors, correct? But still, in addition to that, we do some error detection, maybe simpler error detection at IP router, IP level, and also we do at TCP level some error detection, but they are weak compared to this, but they are acceptable because already we have done a strong error detection, correct? This is something like you write the exam, okay, you carefully write the answer, maybe you check after writing one answer, you check. One answer means one link, okay, something like that. You check, then again you check another answer, okay. If you have thoroughly checked step by step, maybe the final round you want to do one more check, maybe you may have some shortcut method to quickly check. That's another level of checking, right? So, whatever we do at IP level or TCP level, it's an extra level of error checking. So, how we detect the error? How we can detect? When we say detection, okay, the answer is yes or no. We are interested to know whether there is any error or not. We are interested to know how many bits are corrupted, which bits are corrupted. Okay, if you know how many bits are corrupted, which bits are corrupted, okay, bit number 5, bit number 7, then we can correct it. We can do error correction, right? Error correction is a very expensive operation, very complex operation, and impossible for many cases. It's impossible for many cases. We go for simpler approach, error detection. I used to give this analogy, okay. You buy a device, let's say some electronic device, okay. If it's in warranty period, if something is going wrong, that's fine, okay. If it's out of warranty, the question is, maybe let's say you buy a washing machine, okay, at home, it's out of warranty. Now the question is, you want to go for repair or you want to throw it, okay. The repair cost, some dollars are involved, right? If you want to repair your washing machine, you have to call, you have to make some arrangement, okay, you take it, or you have to bring service people, you have to pay them for the transport to inspect it, what's going on. Then they may suggest, okay, you need to replace this part, that part, okay. Then if you calculate how much you will be spending, you will be spending several $100s. So you may decide, no, I don't want to repair it, better throw it, okay, buy a new one, correct? So here also, are we going to use a very complex method to to correct the error, which bits are going wrong, right? For every frame or every packet, if you spend too much time to see whether bit 1 is corrupted or bit 5 is corrupted, that is not acceptable, right? You want to make a decision quickly. The best thing is say yes or no, whether it's a good frame or bad frame. If it's a good frame, pass it. Bad frame, drop it. Or if the protocol allows the other party to request to retransmit, you ask it, send it again, okay? But don't try to correct it, right? So because you want to make a decision very fast. So what type of methods can be used? Of course, we are familiar with at least the parity check, right? Parity check method, correct? So simple method which is normally used within a computer, memory or something, right? We use parity bits within a computer, not on the network. What is done is, let's say we are using odd parity method. So there is a bit stream is there, you want to add some extra bit to make it odd number of bits, right? So when it is received, the receiver will check whether you have odd number of ones, otherwise it may say that that is an error, right? Now what happens if 2 bits are corrupted, right? Again, this will be odd, but the receiver may not be able to correct it, detect it, right? So that's not a good idea to go for it. So another method is something like echo method. Some methods are there. Maybe let's not go into that. You might have studied in school and all, okay? Different possible methods within a computer system, right? Or network also, but they are not useful. So other possible way is, let's say you can duplicate it. Let's say these are the frame bits. The same frame bits you can duplicate it. The same frame bits you can duplicate. Let's say 1000 bits are sent, 1000 bits you duplicate it. The sender will duplicate it. So the receiver will compare the corresponding bits, okay? If both are same, the receiver will say, okay, it's a good frame, otherwise it's a bad frame. Is it a good idea to do that? Yes? Why? Because instead of 1000 bits, now we have to transmit 2000 bits, right? And also the receiver side, it has to compare all these 1000 bits, the pair of 1000 bits. Am I right? That's also needs time. Again, just because this bit is 1, the corresponding bit is 1, doesn't mean that there is no error. Why? When it is corrupted, there's a very, very small probability that the same position, this one has become 0, that one becomes 0. The receiver will think that both are same, correct? It doesn't work out. Maybe for small packet, maybe 2, because if you look at the olden days telegrams, maybe you are all small kids, may not be knowing, right? Those days, we don't have phone, WhatsApp and other things. When we reach our university or this, we go to the post office, we send a telegram to our parents. I reached it, okay? Or if you want to wish your friend, not like the social media application, you have all kind of messages and emojis you send, right? So congratulations message. There are some standard messages, congratulations, birthday wishes and all. Some special code will be there. The post office, you can choose that. They may send special code by their telegraph communication method. But usually what is done is that code will be repeated 2 times just to avoid any error, because when the code changes, the message itself will change, correct? Congratulatory message may be another message there. So they duplicate it, but it's a small number. We can duplicate it, but in the packet you cannot duplicate it. That's not possible. So what we want is this. We want to send a message, let's say n-bit message. We want to add extra, let's say k bits. We want to add extra bits such that these extra bits will help the receiver to detect whether there is any error or not. If you consider parity method, the extra k bit should be only 1 bit. That's not a good idea. If you want to duplicate it, the extra k should be n. That's also not good idea. Okay, but what we want is we want to choose k, a small number, compared to the number of bits carried in the frame. Okay, so see, for example, you take Ethernet. Ethernet can carry up to 1500 bytes. That means 12,000 bits. So Ethernet uses 32-bit extra bits to help detect the error. They are called CRC bits, cyclic redundancy check. We use the method, okay, name of the method to indicate that CRC bits. Okay, 32 bits are used. So 32 is much smaller compared to 12,000 bits. Should be okay, right? So now, how we calculate this number? The number we are going to attach, that is based on a division method. Okay, so we choose. Maybe before I go into the details, let me explain the analogy, okay, how it works. Okay, it's an analogy, simplified example. Okay, it just to illustrate the key idea behind CRC, but it's not the same. Don't get confused. Okay, it's just an analogy. Let's say we want to send some number to the receiver. What the sender receiver can do is they can agree on some divisor. Let's say number 5. They know which divisor they are going to use. So let's say the sender wants to send a message 27. What the sender will do is it will divide this 27 by 5. It will use number 27, 2. It will attach the remainder 2. So it sends 27 then 2 to the receiver. Now the receiver, let's say there are different cases. So receiver might receive as it is without any error, 27, 2. So what the receiver will do, the receiver, it also knows the divisor, number 5 is used. So it will divide 27 by 5 and it will get a remainder. Okay, remainder it gets 2. So the packet also, frame also says number 2. So, okay, good, no error. Let's say it receives 26, 2 because some bit is changed during the propagation. So the receiver will divide this 26 by 5, it gets remainder 1, which is not the same as 2. So this is not a good frame, it's a bad frame. Okay, error is detected, right? That is correct. Now let's say instead of 27, 2, it receives 37, 2. Some bits are changed. When it receives, it gets 37, 2. What happens? What the receiver will do? Receiver will divide 37 by 5, it gets remainder 2, and the same remainder 2 is also carried as part of the frame. So the receiver will say, good, this is a good frame. But is it a good frame? It's a bad frame, right? Because the original data was 27. Does he know that 27 was sent, correct? But why the receiver says it's a good frame? Because the remainder is the same. 37 divided by 5, you get the same remainder 2. Why? What? Okay, where it's going wrong? It's going wrong because the error value, the difference between 27 and 37 is 10, which is divisible by 5. The error value is divisible by 5. Okay, so this is true for other division. Instead of 5, if you use 7, 8, again you can come up with similar examples, right? So we want to use some division method. The CRC uses a division method, but that division method is not exactly this division method. That is similar to a polynomial division method in polynomial theory. Okay, and CRC is going to use a divisor polynomial. We are not going to divide it by a number, but we are going to divide it by a polynomial, and that polynomial we are going to choose such that this kind of situations do not arise. Correct? Intelligently we have to choose. So we want to use some polynomial theory to prove that, okay, if I use this type of division, I can detect, okay, odd number of errors. I can detect single bit errors. Some proof we want, theoretical proof we want, how we are going to, which division, which divisor we are going to use, how the division is carried out. We want some theoretical support. So to do, we borrow some concepts from the polynomial theory, and note that this polynomial theory is used to establish that, okay, this kind of, if you do division this way, okay, your error detection is very strong. It's able to detect this kind of errors, right? But your computer is not going to do the polynomial. Computer is not going to do the polynomial, okay, because what it knows is binary, ones and zeros, right? So you can imagine that if the message is like this, equivalently there's a polynomial. Equivalently there's a polynomial, something like, let's say it's an 8-bit message, x power 7, x raised to the power 4, this. So you can see that this is position 0, x raised to the power 0, this is x raised to the power 7. Wherever there is 1, there are 4 ones, correspondingly there are x terms. This is how we represent a message as a polynomial. Note that your computer is not going to represent this. This is just to give an idea of, okay, the relationship between polynomial theory and the division which we are going to carry out. And this is going to be divided by a polynomial called divisor polynomial. It's a divisor polynomial. This is also called in the literature generator polynomial because it's going to generate a remainder. It's going to generate a remainder. So let's say we are using as an example as a divisor polynomial x cube plus x square plus 1. So this is equivalent to something like 1, 1, 0, 1 because there is no x term here, right? So we use a divisor polynomial. We are going to divide the message by the divisor polynomial. We are going to get a remainder. That remainder is here. The remainder will be added, something like 27, 2, right? 27 is the message, we add 2, right? So now I'm going to explain how the division is carried out. The method is more important. Forget about the polynomial theory, equivalence and other things. So I will be using so many notations here, Rx, Px, or polynomial theory, from polynomial theory. I think if you look at the book also, you will get these polynomials. But if you look at the examples and you can easily relate it, how it works, right? Assume that there is a message. Let's say this is the sender. Okay. So sender has a message m. Let's call it as equivalently there's a polynomial m of x, message m, and it uses the divisor polynomial c of x. C of x is the divisor polynomial. The c of x. Where is it? Okay. Now, what it's going to send is, we are going to send m followed by r. R x is the remainder. The remainder bits, they are added here. That we call it as CRC bits. So if you look at the frame format, you see the CRC bits, right? 16 bits, right? If you look at Ethernet format, there will be 32-bit CRC at the end. So this will be sent to the receiver. This as a whole, we call it as P of x. P of x is m followed by r. Message bits followed by r. Okay? And each has a certain degree. See, when we say this 8-bit number is represented as x power 7, x power 4, this 7 is the degree. I think you should be knowing from the school you might have studied. Degree of polynomial is the maximum power value, right? X power 7. Similarly, so that means when the degree of the polynomial is 7, you have 8 bits. So here the degree of the polynomial is 3. k is the degree of the polynomial because it starts with x cube. For the division, the degree is 3. If the division is 3, you will have 4 bits. Okay. If your divisor, let's say c of x, the degree is k, then you will have k plus 1 bits. Then the remainder degree will be k minus 1. This is something like when you divide a number by 5, maximum remainder is 4. So when you divide a polynomial by another polynomial with degree k, the remainder polynomial, the degree will be k minus 1. It cannot be k, right? Because when you divide it by x cube plus x square plus 1, the remainder will start from x square. It cannot start from x cube or x power 4. Is that fine? That's what it says. So now how we are going to carry out the division? First step, we are going to shift m, the message bits, by k bits. Note that k is the degree of c. We are going to shift it by k, okay, and we are going to we represent this as m of x, x power k, let's say call it as t. When you are shifting it by k bits, that means you are adding k bits, k zeros. Okay. Am I correct? You take a binary number, if you shift it by 1, that means you are adding a 0 here. When you shift left by 2, you are adding 2. So when you are multiplying by, let's say 2 power 2 cube, that means you are adding 3 zeros. When you multiply by 2 power 5, you are adding 5 zeros, right? Similarly, decimal also, when you multiply it by 10 power 5, you are adding 5 zeros. 10 cube, you are adding 3 zeros, right? Similarly, when you multiply by x power k, you are adding k zeros. So that we call it as k. Maybe look at an example. Okay. So this is the message bits 10, 100, 110, and let's say we use c, the divisor, as 1101, that is degree 3, because this is x cube plus x square plus 1. The degree is 3. So the first step is we shift left. This is m. So this is k zeros, because k is 3. This you are multiplying it by x cube. That's what it means. So that is the same as adding 3 zeros at the end. Yes, this is the dividend. You can see this is m followed by 3 zeros. That is the dividend. Got it? So we are going to divide this by 1101. Suppose you use a 5-bit divisor, then you have to add 4 zeros. If you use 3-bit divisor, you have to add 2 zeros here. That's what should be done. Now we are going to carry out the division, and for the division we are going to use modulo 2 arithmetic. Modulo 2 arithmetic is a different arithmetic, but it's very simple for us to do that. If you do normal binary division, it's difficult. Okay, many kids, even we also may find it difficult to divide a binary number by another binary number, because always subtraction and division are difficult compared to addition and multiplication, right? But interestingly, we are going to do mod 2 arithmetic, that is similar to exclusive OR operation. 1 plus 0 is 1, 0 plus 1 is 1, 1 minus 0 is 1, 0 minus 1 is 1, 1 plus 1 is 0, 1 minus 1 is 0. Okay, this is something like an exclusive OR operation. That's what we are going to do. That's an equivalence polynomial theory division. Okay, don't worry about it. We are not looking at polynomial division. That would be extremely hard. So we are going to carry out binary division, but with modulo 2 arithmetic. Okay, how we do this? So first step, add 3 zeros. Then now we are going to divide. So the divisor has 4 bits, so you have to take 4 bits. We need 4 bits. And the first bit should be 1. Okay, otherwise you cannot divide. because the polynomial degree should match. So 1, 1, 1, 0, 1. Now you need to subtract, right? This minus this. When you do subtraction, there is no question of borrowing because we are using modulo 2 arithmetic. Very easy, because when you try to borrow, you get all confusion, right? So 0 minus 1, 1. 1 minus 0, 1. 0 minus 1, 1. No borrowing. You don't need to borrow. Don't do the actual subtraction. Okay. Don't try to convert this into number. 1010 is 10. 1101 is, let's say, 13. How can I subtract 13 from 10? Don't worry about it. There's an equivalent polynomial division. Okay. Just do modulo 2. 0 minus 1 is 1. 1 minus 0 is 1. 0 minus 1 is 1. Then 3 bits. You need 4 bits. So you have to bring this 0 down. 1, 1, 1, 0, 1, 0 minus 1, 1, 1 minus 0, 1. So these two are 1 minus 0, 1 minus 1, 0. Prefix 0 should not be there. So we have only 2 bits. So bring the next bit down. We still have 3 bits, not sufficient to divide. So you have to put 0 in the quotient because we are not able to divide it. So bring one more bit down. 1, 1, 1, 1. So quotient 1, 1, 1, 0, 1, 1 minus 1, 0, 1 minus 0, 1. Again, we have only 2 bits. You bring the next bit down, 3 bits, still you cannot divide it, so add 0 here. Bring one more bit. Now we make 4 bits. 1, 1, 0, 1, 0 minus 1, 1, 0 minus 0, 0, 0 minus 1, 1. So now we have 3 bits. We bring 1, 0 down. 1, 0, 1, 0, 1, 1, 1, 0, 1, 0 minus 1, 1, 1 minus 0, 1, 0 minus 1, 1. So bring the last 0 here. You get 1, 1, 0, 1. Okay. 0 minus 1, 1, 1 minus 0, 1. So you make it 3 bits because this is the remainder. The remainder should be, if the divisor has 4 bits, the remainder will have 3 bits. So it's 1, 1. So you make it 0, 1, 1. So what we are going to do is, we are going to subtract here this 0, 1, 1. Subtracting 0, 1, 1 from this, again it's a modulo 2 arithmetic. 0 minus 1 is 1. 0 minus 1 is 1. 0 minus 1 is 0. So subtraction is the same as addition in modulo 2 arithmetic. Okay. So ultimately what does it mean is, you have the message bits, this is message bits, this is the remainder bits. So you have message followed by the remainders. These are the CRC bits. These are the CRC bits. Is that okay? And this we call it as P. And this will be sent to the receiver. So the receiver receives message bits and the remainder bits. The remainder bits are generated by this division. That is what is done is the adapter. In fact, the adapter uses hardware to do that. So if you remember the operations, the 2 key operations are shift, then exclusive OR. Because modulo 2 arithmetic here is exclusive OR operation, correct? Shift and exclusive OR. So we can use shift register. The bits will be flowing through the shift register, and we can have a few exclusive OR gates corresponding these ones actually. Then you can build a shift register. So when the bits flowing through that, automatically it will flow through shift register everything. When the last bit flows through it, the shift register will have the remainder. So the adapter will let the bits go through the shift register, and the bits will leave, the message bits are sent, and finally whatever is in the shift register will be the remainder bits. That remainder bits will also be sent. That's why CRC, you can see it appears at the end. It's an interesting question, why CRC should appear at the end? Why not put as part of the header, right? Why CRC is put as part of the header? Because we are not doing it in software. We are not first computing the CRC, then inserting into header. That's what we are not doing it. The adapter is sending the bits. When the last bit is sent, automatically CRC is there in the shift register. Okay? It's more like a hardware operation. Earlier I used to teach that shift register design, but due course we added more and more topics, no time for that. But you need to know that there is some hardware design which can do this kind of calculation. Is it correct? Sorry, is it clear? Yes? Please be louder. Yes. Can be corrupted. Can be corrupted. Okay. So we look at the case. The same thing. Okay. Let's say P is sent. P is the message bits followed by the CRC as a whole, correct? During the propagation, some bits may be changed. It could be CRC bit or message bits. Any bit can change, correct? So when the bits are changed, we say that an error polynomial is added. Let's say the fifth bit is changed, something like adding x power 5. Modulo 2 or 5 means x power 5 term was there originally. When it is received, there is no x power 5 term. That means the bit has, okay, it's adding a x power 5 term, right? So if 4 bits are corrupted, you can imagine that there is a error polynomial with 4 terms added to that during the propagation, right? So what is received at the receiver is the original P of x. P of x is this, the message bits followed by the remainder. But when it is received, what it received is P of x plus E of x. If A of x is 0, that means there is no error. As it is, it will be received, no problem. Okay. So what the receiver will do is, it will do the similar division to check if the remainder is correct or not. Again, let's take the analogy. Okay. So let's say 27. When it is received, the receiver will divide this 27 by 5, check whether it gets remainder 2. Note that this is the same as, let's say 27 divided by 5, remainder 2. This is the question the receiver will ask, right? This is the same as 27 minus 2 divided by 5, remainder 0. Both questions are correct, correct? Yes. R can also be corrupted. Yes, R can also be corrupted. I will explain it. Okay, R can be corrupted. Even this example also. Okay, this example I use the same 2 here, right? Suppose we receive 27, but R is 3, correct? The receiver, when we check 27 by 5, it gets remainder 2, but what it received is 3, right? So the receiver will declare this as a bad frame. Actually, it's a good frame, but the receiver doesn't know, right? That the 27 is correct, the error is in 3, it doesn't know. It will drop it. Is that okay? And if you use a longer CRC, higher chance that it's stronger also, the detection is stronger also. Error can be there, but whether we are able to detect the error or not, right? So from the polynomial theory, so there are some theorems. Of course, again, earlier I used to teach some theorems theory also. There are some theorems. If you follow that theorem, okay, then if there is any error in the message part or the remainder part, okay, your divisor polynomial, you have to choose the divisor polynomial in an intelligent way, following some theorems, then most of the errors can be detected. There is no method in the world which can detect all possible errors. Cannot be. Correct? So what we want is this. Maybe first let me see, okay, what the receiver does. The receiver can divide 27 by 5. He can check whether the remainder is 2. That is one possible way. Another possible way is 27 the receiver can divide 27 minus 2 by 5 and it can check whether the remainder is 0. So, what is done in practice in the adapter is, when the receiver receives this, the receiver is going to receive this, right, the message bits followed by the remainder. The receiver will not divide the message bits. The receiver will divide all the bits by this, and it will check whether the remainder is 0 or not. Okay. Please note, at the center side, we add message followed by few zeros, then generate the remainder. The receiver will not generate the remainder. The receiver will divide the entire bit, including the the remainders, and it will check whether the remainder is 0 or non-zero. If it gets 0 remainder, no error. If it gets non-zero remainder, there is an error. If it gets non-zero remainder, there is an error. That is correct. But if it is 0 remainder, 0 as the remainder, it will declare that it's a good frame, but may be good, may not be good. Why? This is the case. If you get 37,2, it declares it's a good frame, but it's not a good frame, right? Why? Because the error value is 10, that is divisible by 5. Similarly, in our case also, okay, we divide, okay, we are checking whether the remainder is 0 or not. The remainder will be 0 if there is no error, that is correct, and the remainder will also be 0 if the error is divisible by C. If the error is divisible by C, that is, here the error value is 10. If the 10 is divisible by 5, you cannot detect the error. Instead of 27, if you get 32, it cannot detect the error because the error value is 5. Instead of 27, if you get 22, we cannot detect it, correct? Instead of 27, if you get 12, you cannot detect it because the error value is 15, which is divisible by the divisor 5. You cannot detect it. Similarly, here, if the error value, the error introduced during the propagation, if it's divisible by C, then you cannot detect the error. That means your test will pass the test, but actually there is an error. This we do not want to happen, right? So we want to choose the divisor polynomial C such that the probability for this case is small, correct? Is that clear? What I am trying to say is, sometimes it may say yes, there is no error, but there may be error. That is possible. Okay. So this slide shows how we can select the remainder polynomial C. There are some guidelines. Okay. It follows theorems from the polynomial theory. Let's look at some. All single bit errors can be detected as long as x power k and x power 0 terms are non-zero. That means if you want to use k bit as the remainder, there should be a term x power k and there should be a term x power 0, 1 should be there at the end. So you have to choose a polynomial such that there is a term x power k and there is a term x power 0. Finally, it should end with 1, that is x power 0 term. If you choose that, it can detect any single bit error. There is a theorem. We can easily establish it. Anyways, it's a network course, it's not a polynomial maths course, so let's not worry about it. Then any odd number of errors can be detected as long as the divisor polynomial which you choose has the factor x plus 1. What do you mean by factor x plus 1? This is something like maybe let's say 24. 24, okay, 1 is a factor, 2 is a factor, right, 3 is a factor, 4 is a factor, 6 is a factor, 8 is a factor, correct? Factor means it can divide, right? So if you choose a divisor polynomial which has factor x plus 1, that means C of x divided by x plus 1 is remainder 0, correct? That means x plus 1 is a factor of C. Agreed or not? When we say x plus C of x has factor x plus 1, don't think that just because we use x square plus x plus 1, it has a factor x plus 1. No. Right? When you divide C of x by x plus 1, if you get remainder 0, then it has factor x plus 1. If it has factor x plus 1, it can detect any odd number of errors. Let's say 5 bits are corrupted. If 107 bits are corrupted, odd number of bits corrupted, it can detect it. There's a theorem which establishes it. Very interesting proof, but we don't have time to discuss that proof and all. Right? Is that okay? But you need to remember this. So suppose I give you, let's say, a divisor polynomial, ask you whether it can detect 5-bit errors. Let's say during communication 5 bits are corrupted. That means odd number of bits are corrupted, right? Whether a given polynomial can detect error, if the question is asked, you need to know how to answer this, right? So you need to check whether the divisor is capable of detecting odd number of bits. How we check? You have to divide this C of x by x plus 1 to see whether there is a remainder 0. How you divide it? Don't divide it in polynomial. Don't divide it in polynomial, okay? You divide it in binary. Represent C of x as a binary. Represent x plus 1 as a binary. What's the binary representation of x plus 1? What's the binary representation of x plus 1? That is 1, 1, right? Binary representation is 1, 1. So divided by 1, 1, if you get remainder 0, it can detect any odd number of errors. Similarly, any burst error means consecutive bits. Okay, if there's a burst of length which is less than or equal to k, that can be detected. K is the degree of the polynomial. And in the literature, okay, you can see there are many recommended polynomials for CRC 8 means it will generate 8-bit remainder. It will generate 8-bit remainder. CRC 10 will generate 10-bit remainder. That means CRC 8 will begin with x power 8, end with 1. CRC 10, if you look at the polynomial, you can Google it or find from the literature or from the internet what is the CRC 10. It will start with x power 10, end with 1. CRC 32, for example, Ethernet, if you look at the actual polynomial, that will start with x power 32, ends with 1. So the degree is 32. That means the divisor has 33 bits, okay, because x power 32. So if you represent this as a binary number, it will have 33 bits, and the remainder will have 32 bits, and the remainder is the CRC. So if you look at Ethernet, that will be 32-bit remainder at the end. Let me stop here. Sorry, I took more time. You try this division. If you have doubts, we can discuss in the next class. Next Wednesday, we will have tutorial 2, so where we will look at some more problems, okay, for the CRC calculation. You can also look at the past year some I posted, in sample quiz paper I posted, so you can try that also, how you can practice it, how to carry out this division, how to get the remainder, okay. Any doubt, students, any doubt? If you have doubts, I can stay here for some more time. Otherwise, see you on Monday. Those students who are absent today, please watch the webcast, okay, before coming to the next class. That would be beneficial. Yes? This lecture is webcast.